You ever stop to think about how the blinding glare coming off a lake is connected to the internet zipping across the entire globe? Well, it turns out that the simple, everyday ways that light bounces and bends, they hold the secrets to some of our most incredible, mind-blowing technologies.
And really, it all boils down to this question. How on earth do we send information, videos, messages, this very explainer, through these tiny little threads of glass? To get to that answer, we first have to understand how light behaves when it hits, well, pretty much anything.
So, let's start with the most basic interaction there is, reflection. I mean, when you look at a mirror, what you're seeing is light performing a perfect, organized, and totally predictable bounce.
But, not all reflections are created equal. Think of light as millions of tiny bouncing balls. On a super smooth surface, like a mirror, they all bounce back in perfect formation, and that's what creates a clear image. We call that specular reflection. But on a rough surface, like, say, a concrete wall, those same balls just scatter in every possible direction. That's diffuse reflection, and it's exactly why you can't see your face in a piece of paper.
And for that perfect mirror-like bounce, there's one simple, really elegant rule that governs the whole thing. The angle the light comes in at is the exact same angle it goes out. Simple as that. It's as predictable as a basketball hitting a polished gym floor.
Okay, but light doesn't always bounce back, right? Sometimes it just plows right through into a new material. And when it does that, something really fascinating happens. It changes direction. It actually bends.
This bending is called refraction. It's the reason why a straw in a glass of water looks like it's broken right at the surface. See, as light moves from the air into the much denser water, it literally slows down, and that causes it to pivot. It's this change in speed that causes the bend. And of course, physicists have a super precise formula for this. It's called Snell's law. Now, we're not going to get into the math, don't worry, but just know this is the rule that lets us predict exactly how much light is going to bend when it moves between any two substances you can think of. All right, now this is where it gets really, really cool. If we combine what we know about reflection and refraction, we can actually solve a very common and, let's be honest, very annoying problem: blinding glare. We've all been there. You're driving after it rains, or maybe looking out over a lake on a sunny day, and bam, you get hit with this blinding sheet of light. Now, this isn't just any old reflection. It's a very specific, very powerful kind. So what's going on here? Why is this horizontal glare so much more intense than other kinds of reflections? Well, the answer lies in a very specific angle of attack. So way back in the 1800s, a Scottish physicist named Sir David Brewster discovered something absolutely incredible. He found that for any two materials, say air and water, there is this one unique angle, we now call it Brewster's angle, where something really magical happens to the reflected light. Okay, so here's the key. Sunlight is unpolarized, which just means its light waves are vibrating in all directions at once. But when that light hits water at Brewster's angle, something amazing happens. The light that's vibrating horizontally gets strongly reflected, that's the glare you see. Meanwhile, the light vibrating in all the other directions, it just passes right through into the water with almost zero reflection. And it just so happens that for an air-to-water surface, like a lake, this special magic angle is about 53 degrees. And yeah, that's a very common angle for how we happen to look at distant surfaces. And this is the genius solution. Polarizing sunglasses have these filters with microscopic vertical slits. They basically act like a bouncer at a club, and they just block all that horizontally reflected glare from getting in. The annoying reflection is just poof, gone. So, we've seen light bounce and we've seen it bend. But what if we could push that bending to its absolute limit and actually trap a beam of light inside something? Okay, so when light tries to go from something dense, like glass, back into something less dense, like air, it bends. But if you keep increasing the angle, you eventually reach a point of no return. This is what we call the critical angle. Let me break it down. Below the critical angle, some light escapes. No big deal. Hit that critical angle exactly, and the escaping light just skims right along the surface. But push it just one tiny degree further, and the light cannot get out. It's completely 100% reflected back inside. This is total internal reflection. It's basically a perfect mirror with absolutely zero light loss. Now, this whole phenomenon of trapping light, it's not just some cool physics trick.
Nope. It is the engine behind some of our most brilliant and most essential technologies.
What you're looking at here is exactly how fiber optic cables work. A pulse of light carrying your data enters a glass fiber at an angle that's greater than the critical angle. It then just bounces perfectly without any loss off the inside walls, zigzagging its way for thousands of miles at nearly the speed of light. It's incredible. And boom, there's our answer. Total internal reflection is how information travels through those tiny threads of glass. We've successfully trapped a sunbeam, or, in this case, a laser beam, and we've put it to work for us. And this one principle is absolutely everywhere. It's what gives diamonds their fire and sparkle. Light gets in, bounces around inside like a pinball because of TIR, and then shoots out the top. It's used in binoculars to flip the image right side up, in medical endoscopes to see inside the human body, and even in the reflective tape on road signs. Oscar Wilde once said, "The true mystery of the world is the visible, not the invisible." And as we've just seen, the simple, visible things like reflection and refraction, they're powered by these elegant, invisible laws of physics that shape our modern world in the most profound ways. So from a simple reflection in a puddle all the way to the global network that connects every single one of us, the behavior of light is this constant, powerful force, which kind of makes you wonder, what other invisible physics is hiding out there in plain sight, just waiting for us to figure it out?